Good morning. Today we will discuss about the new topic, the second semester syllabus, that is electronics. Electronics is a branch of physics which deals with the motion and control of electrons. The physics behind the performance of signal processing devices is also known as electronics. The, in general, we study the motion of a particle or the behavior of the particle in mechanics. So, in the similar way, we study the motion and behavior of an electron in this chapter. So we can say that the mechanics of an electron is called as electronics. So here we are going to study the behavior of a electron under the external fields like electric field, magnetic field, light, temperature. When you supply some energy or some apply some electric or magnetic field, then how the electron behaves. So the electronics is a branch which deals with the motion of a electron or the mechanics of a electron. So the signal processing devices like uh, uh, computers, mobile phones, solar cells, memory cards, pen drives, hard disk, all these works on the principles of electronics. So here electronics has various branches such as digital electronics, micro electronics, nano electronics, optoelectronics, and semiconductor devices. So in we are using this electronics in daily life. So without electronics there is no device in these days. So we can find any electronic device uh, in hospitals, schools, houses, defense forces, artificial satellites, watches, traffic signal, digital cameras, audio players, video players. You can't think our present day's life without electronics. Here we study the behavior of electron in different materials under different conditions. So electronics is a advanced area, right? So in this chapter we will discuss about the matter classification based on their physical existence or physical structures, and we will discuss about the what are the behaviors of an electron when it is in a solids, how it moves, and what are the classification based on the electronic movement and other aspects. Here matter is available, or matter can be exist, and based on physical existence it is divided into solids, liquids, and gases. So solids are the atoms where the fundamental state of matter, this is a solid state, is a fundamental state of matter where the molecules are closely packed and they have some fixed shape and size, and the attractive force between the molecules are very strong in the solids. The arrangement of a space lattice is systematic it has a definite volume. So, for example, you can say the stones, book, iron rod, brick, wooden block, any item you can say the solids are not closely packed, liquids are not closely packed and they don't have any particular shape and size. When you pour in a container, they occupies the container's shape and size. They has a volume. You know the liquids are water, oils, glycerin, and gases. They don't have any particular shape, size, and intermolecular distances are very high, very close, very loosely bounded to each other. So here you see this in the electronics devices in which controlled flow of electron can be obtained. The basic building blocks of electronic circuits before initially the vacuum tubes and diodes, vacuum diodes are there, and valves. These vacuum tubes are very bulky in size. They consume high power, operate generally at very high voltages, and have limited life and low reliability. To see of these developments of modern solid state semiconductor electronics goes back to 1930s. The simply excitation of light, heat, small applied voltage can change the number of mobile carriers in semiconductors. So here this matter is classified or divided into insulators, semiconductors, and conductors. So before we have to study the basics of electronics. Here we have solids which has a fundamental states and the molecules are closely packed. Intermolecular different distance is very less. Here, according to the atom, right? According to the model proposed by the Bohr, the atom is composed of number of electrons moving in a circular or elliptical orbit. Relatively heavy nucleus of proton and neutrons are there. So according to the Bohr, atom has a massive positive charge. The electron can revolve around the nucleus in any orbit, but just in certain definite discrete orbits. Electrons revolve around their nucleus in circular orbits, the centrifugal force being balanced by the electrostatic pull between the nucleus and electron. While revolving these permitted stationary orbits, the electron does not radiate out any electromagnetic energy. So, the permeable orbit or non-radiated path of electrons. If the atom radiates out energy only when the electron jumps from one orbital to another orbital. If electron jumps from higher energy level to lower energy level, then it radiates energy which is equals to photon. So here Thus, the energy, we know the every atom, electrons are moving in an orbit associated with definite energies. These are called as energy levels. These energy levels, but in case of solids, all the atoms are closely packed to each other. So, the energy levels of the outermost orbital electrons are affected by the neighboring orbitals. Affected by the neighboring orbital. So, the electrons in a particular orbital will have slightly different energies. Electrons in a particular orbital have slightly different energies. Since there is a millions of atoms in the solid, the slight difference in energy levels forms a band. This band is called as an energy band. This another orbital electrons of all the atoms from another band, and also shows here you see the valency bands, first band, second band, 1s, 2s, 2p, 3s, right? Here a consider the silicon or germanium crystals. They contains n number of atoms. Electrons of each atom will have discrete energy, different orbitals. These energy levels will be same if all the atoms are isolated. It means that is separated from each other by large distances. However, in crystal, the atoms are close to each other. Therefore, the electrons interact with each other and also with the neighboring atom cores. The overlapping or interaction will be more felt by the electrons in outermost orbitals, while the innermost electrons or core electron energies may remains unaffected. So, the overlapping or interaction will be more in the outermost electrons. For the understanding of electron energies in silicon or germanium crystal, we need to consider the change in the energy levels in the outermost orbitals. Suppose these atoms coming nearer to each other, the energies of the electrons in outermost orbital may change due to interaction between the electrons of atoms. Interaction between the atoms. Originally identical energies in the isolated atoms spread out from an energy band. Similarly to n state, identical energy isolated atoms split into two bands, separated from the one by the energy gaps. So at smaller spacings, there comes a region in which the band merges with each other. Here see this, the band merges with each other at this level. They are splitting into different energy bands, and they get interacted with at some level. The lowest energy state, it splits from the upper atomic appears to drop below the upper state that has come from the lower atomic level. In this region, which is shown by the dotted line, no energy gap exists where the upper and lower energy states get mixed. Upper and lower energy gets mixed in this region. Finally, if the distance between atoms further decreases, the energy band again splits apart and separated by the energy gap. So, total number of available electrons 8n has been reappointed between the two bands 4n and 4n, each in the lower and upper bands. here the significant point is that there are exactly as many states in the lower band are there available valence electron from the atoms. The band, this band, here see the, however the energy levels of inner orbital electrons are much affected by the presence of neighboring atoms. Based on this energy band, the bands are classified into three. The number of bands in solids, as we discussed here, but these three of them are very significant to explain the electrical behavior of the solid. They are the conduction valency band, conduction band, and forbidden band or forbidden energy gap. Valency band. Coming to the valency band. The valency band, the band which is formed by the energy levels of a valency electron. The a band energy formed by the energy levels of all the outermost orbital electrons, or their outermost orbital electrons are called as a valence electrons. The outermost is filled band is called as a valency band. The band is completely filled is called as a valency band. The electrons in this band are fully filled or partially filled. The valency band outermost, the outermost electron of an atom, those in the shell furthermost from the nucleus are valence electron and have highest energy, and they are leastly bonding, having least bonding energy. The band of energy occupied by the valence electron is called as a valency band, and this is a highest occupied band. It may be completely filled or partially filled with electrons, but this valency band never empty. It is here the electrons which are most affected when a number of atoms are brought very close together as during the formation of a solids. The state of lower energy electrons orbitals in the shell near to the nucleus are little, if affected by the atomic proximity. So these valency bands are the energy of electron, valency electron is less. The valency band is formed below the conduction band. The electrons in the valency band are loosely bound to the nucleus, so they are exposed to external energy. They try to move from valency band to conduction band. Here the conduction band is a upper band, which is upper to the valency is called as a conduction band. The next higher permitted energy from the valency. The next higher permitted energy band is a conduction band. It may either be empty or partially filled with electrons. It may be defined as the lowest unfilled energy band. This conduction band is also defined as the lowest unfilled energy band. In the conduction band, the electrons can move freely, and that's why this is known as a conduction. These electrons are known as the conduction electrons. The band formed by the energy levels of free electrons or conduction electrons is called as a conduction band. This conduction band is empty, but when external energy is supplied to the electrons in the valency band, they jump to conduction band. Then these electrons are not bound to any nucleus in the solid. So they are free to move in the solids. Therefore, these electrons are called as a free electrons. The electrons which are in the conduction band are called as a free electrons. So the energy gap between these two, valency and conduction band, the gap between these two bands is called as a forbidden energy gap. The forbidden energy gap is a gap between the higher energy of a valency band and the lower energy of the conduction band. The portion of the energy band structure of a semiconductor or insulator between the valency and conduction band. The gap between the top of the valency band and bottom of the conduction band is called as a energy gap. This is also called as a forbidden energy gap or energy gap. This energy gap is measured in electron volts. In solids, there is no energy gap. So, there is no single allowed energy state in this region. So, this is called as a forbidden region. The forbidden gap is major factor to determine the electrical conductivity of a solid. This band is formed by the series of energy levels above the valency band and below the conduction band. In this region, no electron can exist. When an electron in the valency band absorbs sufficient energy, it jumps to the conduction band by crossing this forbidden gap. This region between this valency band and conduction band is called as forbidden band. This is also called as energy gap. Its value will be large or small or sometimes zero depending upon the nature and depending upon the material. So here the covalent bonds of the crystal lattice have their source in the valency band. If a valency electron happens to absorb some enough energy, it jumps across the forbidden gap and enters the conduction band. In conduction, electrons happens to radiate much energy, it suddenly reappears in the when they get energy from outside or heat energy or electrical energy or light energy, they jumps from higher valency band to conduction band, and then it goes there, it creates a hole. So the neighboring atom enters and fills this hole. The absence of an electron, when it jumps from by absorbing some energy, some electron moves to higher energy level or conduction band. So in the valency band, it remains an empty space. That absence of electron is called as hole. So based on this forbidden energy gap, the material is divided into insulators, semiconductors and conductors. Here conduction in electrons are found in freely and flow in the conduction band. Holes exist in and flow in the valency band. Conduction electrons are found in and freely flow in the conduction band. Conduction electrons found in conduction band and they flow freely. And holes exist in the valency band and flow in the valency band only. Conduction electrons move almost twice as fast as holes. So here the electrical conduction property of a different elements And compounds can be explained in terms of the electrons having energies in the valency and conduction bands. The electrons lies in the lower energy bands, which are normally filled, play no part in the conduction process. So here we, depending upon the conduction property of different elements and compounds, we can um, differentiate this as insulators, conductors and semiconductors. So insulators are those materials which valency electrons bond very tightly to their parent electrons. The material which with a high forbidden energy gap, it is more than the 5 electron volts, is called as insulators. They have Insulators have high resistivity. These electrons are bound tightly to their parent atoms. Thus, they require very large electric field to move them from the attraction of their nucleus. So, in other words, we can say the insulators have no free charge carriers available with them under normal conditions. The normal conditions, they don't have any free charge carriers or the free electrons. Here charge carriers are the free electrons. So we can say that in terms of energy band, the insulators have a full valency band and insulators have a empty conduction band. Insulator have a full valency band and empty conduction band. So there is no free electrons. A large energy gap is there in between the valency and conduction band. Due to this large energy gap, to move electron from valency band to conduction band, we require very high energy or very high electric field. It is not possible in practical. At ordinary temperature, the probability of electron from full valency band gain sufficient energy so that to go to the jump from the valency to conduction become available in the conduction band. The examples for the insulators are wood, diamond, paper, mica, plastic. All these comes under the examples for the insulators. So there is a large energy gap between the conduction band and valency band. This conduction band is fully filled in the insulators and valency band is fully filled and conduction band is totally empty. So we require a very high amount of field or energy to move electrons from valency band to conduction band. That's why there is no free electrons to move, so they do not conduct electricity. Their resistivity is very high. So their resistivity of insulator, you can say that the resistivity is very high for the insulator. So insulator resistivity is around 10 power 11 to 10 power 19 ohm meter. The conductivity is very less, that is 10 power minus 19 to 10 power minus 11 to 10 power minus 19. So here the insulators, the value of this rho and conductivity are indicative of magnitude, could be go outside the range also. So next, conductors. The conductors are those having plenty of free electrons are available for the electric conduction. So they conduct the electricity. Due to the availability of free electrons, plenty of free electrons are available. In terms of energy band, there is no gap between the conduction band and valency band. This conduction band and valency band are overlapped here. This is for conductors. So the electrical conductors are those which have overlapped valency and conduction band. These are the conductors. In fact, there is no physical distance between the two bands. Here the availability of large number of conduction electron and the absence of forbidden energy gap in a good conductor, there is no structure to establish hole. So the total current in conductors is simply a flow of electron. It is exactly for the reason that the existence of holes was not discovered until the semiconductors was studied thoroughly. Here there is no forbidden energy gap in between the conduction and valency band, and these valency band and conduction band are overlapped. So total conduction of electricity is done by the electrons only. The electrons from the valency band moves freely to the conduction band. There is plenty of conduction electrons are available in the conduction band. When some external field is supplied, electrons will move easily the valency band. They jump to conduction band. These electrons are not bound to any nucleus in the solid, so they are free to move. Therefore, the electrons, these electrons are called as a free electrons. Examples for the conductors are the silver, copper, aluminum, iron, and other materials. Due to the large number of available electron, the conductivity is very high and the resistivity is very low in the conductors. So next is semiconductors. The semiconductor material is one whose electrical properties lies between the insulators and the conductors. For example, germanium, silicon, gallium, graphite are the semiconductors. In semiconductors, the energy gap is very less. The forbidden energy gap is very less. So when you give some little amount of energy to the electrons in a valency band, they easily jump from valency band to the conduction band. So in terms of this energy band, the almost empty conduction band and also fully filled valency band with a narrow energy gap is there in the semiconductors, that is nearly 1 electron volt. The electron volt is less than, the energy gap is less than 3 electron volts. The more than 3, it is considered as a insulator. So for example, at room temperature, silicon's forbidden energy gap or energy gap is 1.12 electron volts, and at room temperature, germanium forbidden energy gap is 0.67 electron volts, and gallium 1.42 electron volts. So semiconductor can be defined those materials which have almost an empty conduction band. Here, an empty conduction band and fully filled valency band. The valency band in the semiconductors is fully filled and the conduction band is empty, and very narrow energy gap between the valency and conduction band is called as a semiconductor. The conductivity or resistivity of these semiconductors lies in between the conductors and insulators. At 0 degree Kelvin, at a 0 degree Kelvin, there are no electrons in the conduction band and the valency band is completely filled. With increase in the temperature, the width of the forbidden energy gap is decreases. When you increase the temperature, forbidden energy gap decreases, so that some of the electrons are liberated into conduction band. So the conductivity of the electron increases with the temperature. Here resistivity decreases due to the reduce in the energy gap. So such departing electrons, whatever the electrons moving to the conduction band leaves behind positive holes in the valency band. When the electron jumps from a higher energy level to lower energy level, they move to higher energy. In semiconductor, they move to higher energy level. For example, here electron is here, it moves to upper state, then in this valency band empty space available, it leaves a hole. The conductivity of semiconductors increases with temperature. So when the electron moves from valency electron band to the conduction band, it leaves a positive hole in a valency band. So here the absence of electron in the valency band is called as a hole. Here some semiconductor current is the sum of the electron and the hole current flowing in a opposite direction. So in semiconductors, the charge carriers are electrons and as well as holes. Hole is a empty space left by the electron which moves from lower energy valency band to the conduction band. When the in valency band, see here, if this is the valency band and electron goes to higher energy level, it leaves a hole. This hole is filled by the neighboring electrons. It is filled by the neighboring electron. So the electron movement and the hole movement is opposite in the direction. So in semiconductors, the charge carriers are the holes. The current can be flow through the holes and also by the electrons. So energy gap is very low in the semiconductors, and the electrons fully filled in the conduction band and fully filled in the valency band, and the conduction band is totally empty. When we give some amount of electric field or energy, the electrons from valency band moves to conduction band. then they are free to move. It leaves a hole in the valency band, so that in semiconductors uh, conduct the electricity through holes and also holes. Holes and electrons are the charge carriers in the semiconductors. The semiconductors behaves like insulators at low temperatures. However, low temperature, the valency band is completely filled and conduction band is empty. So, semiconductors behaves like an insulator at low temperature, and they conduct more when the temperature is raised. When the temperature increases, the resistivity of semiconductor decreases with the temperature. Here we have the energy levels. So different energy levels. The energy level is energy gap is more in insulators and less in the conductors. But the energy gap, here the highest level that an electron can occupy is at absolute temperature is called as a Fermi level. The electron occupies the highest level at absolute zero temperature is called as Fermi level. In general, this Fermi levels lies between the valency band and conduction band, but it changes its location by changing in the temperature. So in semiconductor, the probability of occupation of energy levels lies in a conduction band and valency band are equal. Therefore, Fermi level for the intrinsic semiconductors lies in the middle of the forbidden energy gap. So, for the energy band position, the lowest energy in the conduction, this forbidden energy gap lies between the middle for the semiconductor, it lies between the middle of the valency and conduction band. The Fermi level is the highest energy level that an electron can occupy at 0 degrees Kelvin temperature. This is considered as the hypothetical energy level of electron. The Fermi level can be considered as the hypothetical energy level of an electron, that is the highest. Here, if we consider the electrical potential energy of a conduction electron is uniform throughout the lattice. If the electrical potential energy of a conduction electron is uniform throughout the lattice, if you set this potential energy to equals to 0, that mechanical energy is entirely in the form of kinetic energy. Then the level of bottom of the partially filled band corresponding to electrical, this total energy equals to 0. So the highest energy occupied by the electron in this band at absolute 0 temperature is called as a Fermi level, and the energy corresponding to this Fermi level is called as a Fermi energy. The Fermi energy for copper is 7 electron volts. The electron speed corresponding to Fermi level is called as a Fermi speed. The energy corresponding to the Fermi level is Fermi energy. The speed of electron corresponding to the Fermi level is called as a Fermi speed. So here we discuss the basics of electronics, fundamental concepts of electronics, right? So conduction band, valency band, forbidden energy gap, Fermi level. Based on this forbidden energy gap, energy levels, the material is divided into insulators, conductors and semiconductors. In next class we discuss about exclusively about the semiconductors, how the what are the types of semiconductors, how they behave when some impurities are added, how the resistivity of a semiconductor increases with adding some impurities, what to do to increase the conductivity and the performance of electrical device uh, using these semiconductors. These topics will be discussed in the next session, right? So in this session we discuss the major minimum basics required to understand the electronics, right? Thank you very much.